Right, so this is task 2 now, the design of the closed loop PI control system using Nyquist method. And we're having a proportional plus integral controller, which is classically given by Kp plus Ki over S. But in Nyquist, when you want one parameter to change, so we're going to have to take the Kp out as a common factor and write it as Kp, open brackets, 1 plus 1 over TIS. This is a sort of fairly standard format for a PI control. This is one format, this is another. I suppose this one's in, you could argue, in time constant form, whereas that one's in pole form. And in this controller, U is the output from controller, E is the error. And our job really is to find Kp and Ki. And the method obviously comes from Nyquist. This is a picture of Harry, and he was inventor of the Nyquist stability test. And his thinking was, it was a frequency domain test, and we had an open loop transfer function which has a set of zeros and poles, and the open loop stability equation is the bottom line given by here. If we've got a closed loop system, then the closed loop system can be given by 1 plus kgs equals 0, and when we calculate that, we get the ps plus kzs on the top, which happens to be the closed loop stability equation, divided by ps. So in the Nyquist stability theorem, we look at the ratio of the closed loop stability equation to the open loop stability equation. And on the basis of that, he comes up with this simple little formula for assessing stability, which is n is p minus z. P is the first thing I always work out, the number of open loop and stable poles. Z is the number of closed loop and stable poles, and ideally we want Z to be 0, because if Z is 0, this closed loop system is stable. And then N is the number of anti-clockwise encirclements of the -1 point by the Nyquist plot. So this is, we have to get this from plotting a polar plot and a mirror image of the polar plot. So, and when you compute these things, you always work out P first, N second, and Z third. And his underlying trick, I suppose, was that this equation here could rewrite as this equation here. And so rather than looking at the closed loop system, you could just look at the open loop system relative to the -1 point. So that's why the Nyquist plot is always encirclements of the -1 point, because it's actually looking at this equation here. So for our particular application, which is applying the Nyquist stability criteria to the process trainer, the open loop number of poles is 0. And therefore, going back to this equation here, P is 0, and we want Z to be 0, so therefore N has to be 0, which means now that the Nyquist plot has to be to the right of the -1 point. If it's to the right of the -1 point, it will be stable, and handily enough, if we measure this distance here and call it A, that's from the origin to where the Nyquist plot crosses the imaginary axis, or the real negative axis, then we can work out the gain margin, which is just 1 over A. And the gain margin is the amount we could increase the controller gain by to move this point to here. So if I multiply A by 1 over A, it becomes 1, so that point moves to the -1 point. So that's the thinking behind the stability test using Nyquist, that we measure something, this distance here, which is called A, and we then convert that into 1 over A as the gain margin. So this is a design now based on gain margin concepts. So the gain margin is 1 over A, so we measure this distance here from the polar plot, and that gives us A, and then the gain margin is 1 over A. And we can have the gain margin is defined as the amount, and we can have to increase the gain in this controller here to move that point from there to the -1 point. And so we can work out, there's various ways of working out gain margin. We could work it out using Bode plots, and it always occurs when Bode plots, it's when the phase is -180, because the phase there is -180. Or we can just work out 1 over the modulus of the gain at this point here. They have two little symbols in here. This is PC is the phase crossover, and this one here is called the gain crossover. Now, let's have a look at effect of gain margin on system performance. So we could choose now different gain margins and see how the system performed. So we're going to set the control system now to have a gain margin of 2, gain margin of 4, and probably 3. And what we should see is with gain margin of 2, the gain is quite high, and we could have overshoot in the system. With a gain margin equal to 4, we'll get a slower response and get much less risk of overshoot. So that's what we're looking for, and typically this is what you might see in a closed loop system response for different gain margins. Gain margin of 2, quite an oscillatory response. Gain margin of 2.5 would be less gain, it's not quite as oscillatory response. Gain margin of 3, again not as much oscillation. Gain margin of 4, hardly any oscillation at all. So as we increase the gain margin, the control system performance steadies down. If we go much bigger than 2, it's going to be too oscillatory. If we go bigger than 4, it's going to be too slow. So most gain margins are set between 2 and 4. And let's just have a look now about how we could do this. Okay, so here's the Matlab code now for proportional control only. So for my example, I'm going to assume my K is 2.2, TP is 0.6, and TD is 0.4. So I need to use that now, those parameters, to enter in the transfer function. So I'm going to do that as the numerator as K, the denominator as TP1, so that's going to be TP1. And then I use the TF command with ND, but I now use a special command called input delay, which is in quotes, and then comma TD with a time delay in there. Now these quotes, if you copy this code from PowerPoint into Matlab, it puts a different quote in. It doesn't like it, but if you then type out the quotes and put the normal quote in Matlab, the code will run. So if we run this code, we will get this Nyquist plot here, and from that we can see the point here where we can measure the gain margin. So that distance there is 0.73, so the gain margin is 1 over 0.73. Now when we come to do the PI controller, this time we've got the same system in here, so that's the same as exactly the same code down to here as we had before. This time though, we're choosing Ki as 1 over Tp. That's our design, that's what we've set Ki to be, and then we've got to put this bit in now. So this is going to be 1 Ki as the top line and 1 0 as the bottom line. Then sys2 is that transfer function of numerator and denominator. Then sys3 I get by multiplying this by this. I then do a Nyquist, and I've used an axis command here just to make the graph on a nice scale for us. And if we then measure from here to here, this time it's by clicking on that point there, it's 0.933, so the gain margin is 1 over 0.933. So as you add integral action in, what tends to happen is the gain margin reduces. So this is quite close to 1. So if we chose a gain of 1, this system would be almost marginally stable. So let's have a look at the calculations now. So by measuring that distance, the distance from there to there, remember that we're calling that A. So if we measure A, then the gain margin is 1 over A. So in this case, it's 1 over 0.933, which is 1.07. So that's going to give you, now to get a gain margin of 2, you just divide this number by 2. To get a margin of 4, just divide it by 4. So it's very simple. Once you've got this number, to get your other gains for different gain margins, just divide this by whatever gain margin you want. So that becomes super simple, doesn't it? So then that gives us a way of getting the Nyquist PI gains. Ki is 1.66 all the way through, and the gain margin, so it's going to be the first one, this number here is this number here divided by 2, which comes out as 0.535, and when it was 4 it came out as 0.267. So you could work out these just by dividing the numbers by the appropriate numbers here. So that then gives you your Nyquist designs. Right, so now we're on to task 3, which is using the Ziegler-Nichols tuning rules and the Tirius-Lubin tuning rules. The Ziegler-Nichols tuning rules is probably more famous than the other one. They were invented around 1945 and still half used today. They had two methods. The one we're going to look at today is called the continuous cycling method. And the idea behind this is that we take the system and we put it under feedback control. So we put it under feedback control and we keep on increasing with no integral in, and keep on increasing the gain until it becomes marginally stable. And then that tells us then that's the gain that makes it go unstable. So that is essentially the gain margin. So then what you can do then is, having got your gain margin, you can then halve these numbers. So you can see what a gain margin of 2, you would halve that number, and then that would give you a gain margin of 2. You can also, off the graph, you can measure the period, which is the time from peak to peak. And what I did is I took about 6 peaks, so to get me a little bit more better of an average when I did the calculations. So let's go back to this then. So what we're doing is we're going to look at this sort of result here. Now we can get this from two sources really. We can get it from plotting the Nyquist plot of this. This is the open loop system under proportional control, and this distance here, when it crosses here, this is the this is 1 over the gain margin. So this came out at about 0.73. So the gain margin will be 1 over 0.73. That's using the same sort of code we had here, and it also gives you the frequency at which this point is as well. So you could work out the ultimate period as 2 pi divided by that frequency. So so there's two ways of getting at these answers really. The Ziegler-Nichols and Tirius-Lubin rules look like this. So if you're doing pi, it's 0.4 times the gain that makes it go unstable, and ti is pu over 1.2. Now remember, ti is 1 over ki. Remember, there's a sort of complication here, not very complicated one, but they do it in time constant form. This is done in pole form. So so your ti is 1.2 over pu over 1.2. So ki would be 1.2 over pu. They sort of invert, and similar here, ki would be 1 over 2.2 pu. So just bear that in mind for a little bit later. And in general, you say that the Ziegler-Nichols method has got slightly bigger gains. That's giving you closer to gain margin 2 results, whereas the Tirius-Lubin one's got slightly smaller gains, which is giving you more like a sort of 0.3 gain margin, or 3 gain margin, or 0.3. So what we're doing here is we're looking at the system for when it goes marginally stable by changing the gain. So what I've done is I put the system under closed-loop control. These are the parameters that I've got from my system identification. Put the integral gain to 0, and then just increase this until it's gone marginally stable. And I got a k of 1.47. And I measured 6 PUs, from which I got PU was 1.3. So I could then put these numbers now into these formula. So when I do that, the Ziegler-Nichols gain is 0.45 times 1.47. Remember, the gain here was 1.47, and the table says 0.45. So it's 0.45 times 1.47. That comes out as 0.666, and the Tirius-Lubin method is 0.31 times that, which comes out as 0.46. Then the Ziegler-Nichols gain is 1.2 over pu. So my pu was 1.3, so that becomes 0.93. And for my other method, it's 1 over 2 pu, so it's 1 over 2 pu, comes out as 0.35. So this is coming out a bit low for me, but there we go. So then, when we've done that, we've then got a 6 controllers now that we've designed. So these are my values, but you'll have your own values in this table now, which will be different to mine because you won't have the same transfer function. But you could, my values are correct. So if you wanted to run my example first, just to make sure you understood everything was okay, that might be a good trick. So then what we can do is we can now put these gains now for the different designs into our simulation. So this is going to be the simulation. That's the KP, that's the KI. There's the KTP. Into there you type the TD. That's the thing we're going to simulate. So in my particular case, it was 2.2, 0.6 and 0.4, and then I've put some gains in here now. So click on these boxes, put in the gains. So the first one I'm showing you now is the Nyquist gain margin 2. So this one's quite fast. It's got quite a bit of overshoot, a bit of undershoot. Not a bad design, just a little bit too much overshoot for me. Gain margin 2.5, this is the next design, so I've changed the gains. And this is my design for gain margin 2.5. So this is better than this one because it hasn't got as much overshoot and undershoot. This is quite a nice design, really. And then for gain margin 3, so as you reduce the gain margin, the overshoot gets less. So I get to gain margin 4, it's a bit too slow, really. So that's highlighting now, I think, quite nicely what's going on. Gain margin 2 is always a little bit too fast, and gain margin 4 is a bit too slow. You're going to live somewhere in between those. So it depends on what you want. You might go for 2.5, or you might go for 3. If it was, like I say, a flight control system like altitude hold, pitch roll, yaw dampers, that type of thing, you'd probably go for gain margin of 2.5. It feels like an engine control where you don't want really overshoots, because overshoots mean over temperatures, over pressures and engines. You'd probably go for 3 to 4, so a bit more conservative if you don't want overshoots. But that just depends on the type of system you're controlling. So that's where we're up to. So the next section we're going to look at is task 5, which is the real-time comparison. So you've got your gains here now, and you can now, I will, for your particular example, I'll have given you a set of same set as these graphs, which look a little bit like these and these. I'll have given you those. These are the Cyclo-Nichols and Tirias-Lubin graphs as well. So the Cyclo-Nichols is looking quite similar to a gain margin 2. This is looking like a gain margin of 4 or 5, isn't it? This is quite a detuned controller. So they've like detuned theirs, and they've got high performance. This is low performance. So I missed that one out, unfortunately, but we did get it in the end. So then what we're going to do is I will give you some of these results. That's these graphs, these 6 graphs, and you can then compare them with your 6 graphs. And that's going to be your comparison then with the real-time results. So that's, and I'll do some extra things on this. I'll do a little video next for you to see, but this is the PowerPoint presentation part of it. So the submission will be on Turnitin 3 weeks after you've done the lab, and the submission time is 4 o'clock. So we'll do a little bit more now on some of we'll just show you how to run some Matlab code and things for doing some of the details of this. Okay, so this is Matlab running, and I'll just show you how to run some of the programs for you to see how to do different things. So the first thing we'll need is a program to say to plot a not doing very well here. Program to plot need a program to plot a Nyquist plot. So just zoom up here. So here's the first little program here for final last. So you could copy this. So just do copy. Now watch, you have to watch these little quotes here. And I'm going to go back to Matlab, and here's a Matlab command environment. I'm just going to paste it in there. Now it's not going to like this because these quotes are wrong, so I just change it to a normal quote, and when it goes, it'll go blue. There we go. So this is the site. So you put your K, TP and TD in there, and then go on to edit and then run, and you'll get now it's a bit slow. Here it is. Here is your Nyquist plot, and you're after this point here. So just click on that with your mouse. Your mouse can move the mouse around. Click on there, and it gives you the value 0.722. Then if you go on to File and or even Edit, Copy Figure, you can then paste that into Word using the normal copy and paste. So that could be your first graph you're going to get, and you need that number there. That's a handy number in there, and that frequency as well if you wanted. Might need that. If we go back to the next program, that's this one. It's a bit more complicated one. This is doing the PI one now, remember? So we could copy that one in, do that copy, then go back to Matlab and get rid of all this stuff. So just delete all this, zoom, and then paste this one in. And now do the same thing here again. It's a bit of a nuisance this, isn't it? But anyway, it's not too bad. Saves typing, isn't it? So there's our new program now. So just run this one, and this will give us our new plot, and we can see now it's quite close to 1. So let's click on that point there, and you see it's 0.93. There's the frequency. So this is giving us, remember, from there to there is 1 over the gain margin. So the gain margin is 1 over 0.93. If it gets to 1, that goes a bit bigger, goes on that side. It'll start making encirclements, so it'll go unstable. Again, you can do Edit and Copy Figure, and you could paste that into your report quite happily. Now, once you've got our, that's the first thing we do. We then, going back to our table here, click on the wrong thing, there, too many things going down. By this stage, you'll have now your little table of gains here. So you'll have some numbers in here. So you can now try those out now. And we've also got the table of gains from our cyclo-Nichols design, and the table gains from our Tirias-Loop. And so we've got all these gains now. So we've got this big table of gains. So we can now try these table of gains out in our simulation. So again, if we go back to Matlab and go on to Home, and then go into Simulink, and then you can load in or produce this little program here. So remember, my time delay is set at 0.4, so you've got to put that in, and then I can try out different gains in here. So if I go for my Nyquist, say gain margin 2, I can put in 0.535, and in here I can put 1.66, and then if I click on the Run button, I can then, should make a funny little noise when it's finished. There it goes, and then double click on my thing, and there's my result. And if I go into Files, Copy to Clipboard, again I can copy that and paste it, and when it pastes it, it changes the black to white, so you get a nice little graph. So that's your gain margin 2. If you drop your gain margin to 4, this drops down to 0.267. Your numbers will be different because I've chosen quite a big gain here, just to make mine different to yours. And again, we'll get a much slower, this is gain margin 4, non-overshooting, slowish response, which is what I was hoping to get, really. So you can then choose different gains in here, and you can work through then all of your different designs here. If you wanted to look at the do the continuous cycling test, you'd put this as 0, so put that as 0, and then you'd run this as a simulation. You'll see what happened. So it's stable, isn't it? So we can put this gain up now. So let's put it up to, say, 1 and run it. So now it's still stable. We just keep on increasing this now until it becomes marginally stable. 1.3, run it. Still stable. Let's try 1.6, shall we? Run. This time unstable because it's going away, so it's somewhere in between. So double click on that again and choose, say, 1.5. This method's not as exact as the frequency domain because simulation isn't always 100%, so it's probably not bad, that one. Just going away slightly, isn't it? So probably that's why I got my 1.48 or 1.47 even from. That's how I got my 1.47, was just by using this, and then that was giving me my marginally stable case, and then I was measuring then from there to there or there. I measured from there to there, and so there's 1, 2, 3, 4, 5, 6 of them, and took an average to get PU. That's the time from peak to peak. So there's how you can do some of your calculations now in Matlab and Simulink, and that should be fairly straightforward. If you want to get this diagram into Word, I prefer print screen and then shrink it on. You can do another trick as well, which is there's a way of saving this diagram, but I can't remember how to do it. Just a minute, let's get Word going. Now we might get Word going. Open this up, paste it in there, and then just do picture format, crop, and then just crop it in. Like that, and then you've got a nice little diagram which you can, it's too big now, but you can, nice diagram you can control the size of. That gives you probably the best way of getting your plot diagrams into your report. So hopefully you found all that useful. There's some more real-time trials to come next, so I can show you how this actual system runs in real time as well.
Right, so here we have some practical results, so I'm just going to run through these as we go along. So my first one was for my Nyquist gain margin of 2. The gain was 0.535 and Ki. Now I've had to work out Kp times Ki, but it was, the correct value was these numbers. Yes, this is my Nyquist gain margin of 2, as in my results in the video. So you can see not quite as much overshoot maybe as we were expecting, but not too bad. Nyquist gain margin of 2. Let's go next one. Nyquist gain margin of 2.5. This is going to be 0.428. This next one is Nyquist with a gain margin of 2.5. So not quite as much overshoot on this one. And next we're going to go for Nyquist gain margin of 3. So this is Nyquist gain margin of 3. Here we go. So as you get more gain margin of 3, it's not having really that much overshoot at all. So between 2 and 3 is where you want to be. If we go for a gain margin of 4, this is Nyquist gain margin of 4. So look at that one. So this time you can see it's definitely slow and sluggish, but it's quite a nice response for a system response. It's quite nice here. Let's go for our Ziegler-Nichols next. This is our Ziegler-Nichols PI now. This is quite similar, should be quite similar to gain margin of about 2. So I've got a bit of overshoot, a bit of undershoot. Ziegler-Nichols gain tends to be a little bit fast. So that's our Ziegler-Nichols gain of design. And our final design is a Tubus-Lubin, which is this one I think is a bit disappointing. Let's have a look at it now. It was disappointing when I looked at it last. So as you can see, it's a little bit slow. Comes up a bit like what I did in the simulation. It's a bit slow picking up here. It does pick up eventually, but it's a little bit on the slow side. So that's our designs for those. Now let's look at continuous cycling. So if we start off with K, let's say 1 and 0, this is where we just change the proportional gain until it goes into a limit cycle to find out our gain, ultimate gain. So you can see this one is, that's stable, isn't it? So 1 is okay. So if we increase the gain a bit more, let's go to 1.2, 0, 0. So remember, this is continuous cycling. We increase the proportional gain only till the system becomes marginally stable. So it's a bit more bouncy, but it's still stable, isn't it? Still, those oscillations are decaying. So if we go for K 1.4, 0, 0. It's a bit too much sunlight in my garage at the moment. It's not normally sunny. So this one's not almost there, isn't it? You can see it's still decaying, but that one's not far off, is it, from being marginally stable. So if I choose a K now of 1.600, so this time it's definitely gone into and if anything, the oscillations are slightly growing now. So we could go for 1.500. So it's probably going to be about 1.5. Let's have a look. This one now is just about marginally stable. You can see some sort of sustained, slightly decaying, but at 1.5 it's almost there. And remember, my value was 1.47. So 1.5 and 1.47. I must tap myself on the back and say, quite a nice little job. And that's how we could find. We could measure the period from there to there or there to there to get PU, couldn't we? We could measure off that to get PU as well. So that's how we could use our continuous cycling then to get a gain. So it's 1.5, so we'd halve 1.5 to give us, or multiply it by 0.45 if we're using the Nyquist, or if we halved it for a gain margin of 2, that would give us a gain K somewhere in the region of about 0.6, and probably what we need then is about, on my system, probably about 0.9 there. This is roughly a quick fix to a gain margin of 2, and it's not brilliant, is it? But anyway, you can't win them all. Anyway, that's some real-time results for you to have a look at as well. I'll supply you as well with these for the designs and the models that you've got, so you've got something to compare with, but all this set is for the ones I did. So from my results, I would say there's quite a good correlation between theoretical and practical results. I can change the rig a little bit by messing about with some dials on it, so you won't have quite the same transfer function. So good luck with the lab. I'm just going to, at the end, I'm just going to give you an overview how to write the lab up. So that's the last thing to look at, and then you've watched all the videos.